And so now what we want to talk about is the beginning of a major area in first year physics, and that's regarding circular motion. We want to look at the kinematics of circular motion and eventually other aspects of circular motion as well. Forces related to moving in a circle and momentum and energy even. But for now we're going to stick with the motion and specifically the kinematics. And so we've already covered two types of kinematics. The one that we haven't done is circular motion. We've dealt with the motion of an object in this direction, the horizontal, an object in this direction, the vertical, even along the slope, still was one-dimensional motion. Then we got into two-dimensional motion, and that was our look at projectiles, and that was something moving through the air in the X and the Y direction. And so it has that parabolic shape to it, and so we needed to deal with its X and its Y components. Now we get to our second type of two-dimensional motion, and this is circular motion. And circular motion, we're going to find out, obviously, I think by looking at it, is occurring in two dimensions. And it's very, very different than parabolic motion. The motion of this mass on a string here can be described in a couple of ways. We are moving around a circle, and that means that we have a fixed radius. That is, the mass is moving around a center with a single radius. We could have a vertical circle like this. We could have a horizontal circle like this. But what we do need to do is make sure that we're a fixed radius away from that center. And then what happens? Are we going to have objects that start slowly but then speed up, or the opposite, speeding up and then slowing down? Maybe we'll have circular motion that is uniform, constant. All of these things we're going to have to investigate when we look at the kinematics of circular motion. And so let's start by defining circular motion a little as the motion around a circle with a fixed radius so that is the distance of the object as it's going around a circle doesn't change. But when we're talking about circular motion, we don't need to think about going around one full circle. Our object can go around many times, hundreds of times, thousands of times, or even part of a circle. Going around a quarter of a circle, like my fist here from here to here, is circular motion. That is part of circular motion. You don't need to travel a full circle for circular motion. And now you can think of all types of motion that qualifies as circular motion. The hands on a clock, a car getting off of an exit ramp from a highway, a NASCAR race, right? Those racing where they go around and around and around. There's plenty and plenty of examples like that. As long as we have part of a circle's motion, let's say from here to here, and our radius is not changing, we have circular motion. One type of motion we didn't mention is, what if the center of the circle is within our object itself? Like, let's pretend for a second, let me see if I have got another object that I can demonstrate with. Let's say this object right here, this hockey puck. What if we rotate it around like this? Is this circular motion? I mean, it's not going around like this in a traditional sense. It's going around through a center, through a radius, basically that is as big as the object itself. And so it's just rotating around like that. Does that count? Absolutely, it absolutely does. And we'll see lots and lots of examples of that. So rotation around some point that's outside the object, but also sometimes rotation inside, basically spinning, is going to be a type of circular motion that we will consider. All right, so let's get started with the easiest type of circular motion to begin with. And that would, of course, be a circular motion where there is a constant speed, where our object is not speeding up or slowing down around the circle. We're going to define uniform circular motion as circular motion with constant speed. Now, I am using the word speed here very, very deliberately. I did not say velocity for a very good reason. So this is circular motion with a constant speed. And the reason we have to make that distinction between speed and velocity is because velocity takes into account direction. And our very simple idea of what velocity is means that this object, as it spins around, is constantly changing its direction. If we use a standard XY axis, at any point along this circle, our object is going a different direction. Let's pause it at a couple of points and take a look. So for example, as it goes around, when it gets to here, it's going up. The direction of its velocity is tangent to the direction of the circle that it's moving. So stop right there, it's going straight up. Stop up here at its peak, it's going that way. Over here, it's going down, etc. And at every single point along the motion of the circle, it's going at a slightly different direction. And so what that means is, even if the speed is constant, the velocity is not constant because the direction is not constant. Velocity is a combination of direction as well as the magnitude of the velocity or the speed. And so they must both be constant to qualify as a constant velocity. And that's not possible in circular motion. Clearly, our regular constant velocities, you're going in the same direction at exactly the same speed. That is not what is happening here. So let's instead write that the magnitude of the velocity is constant. And additionally to that, as I've shown, the direction is constantly changing. All right, so now that's a very, very curious occurrence because we have a definition for acceleration. We know that the acceleration of an object is related to its change in velocity. And so the question is, if the velocity's direction is changing but its magnitude is not, is there an acceleration? Is there an acceleration of this yo-yo going around a circle, even though right now we're going at a constant speed? So I have a constant speed here. Usually we think of, well, if the speed is constant, then the acceleration should be constant. That's incorrect. What you should be thinking about is velocity. If the velocity is constant, then the acceleration is zero. There is no acceleration, but it's not related to speed, it's related to velocity. And so the velocity in this motion, even though the speed is the same, the magnitude is constant, what is not constant is the direction. And so, if the direction is constantly changing, does that mean that I have an acceleration? Yes. Our velocity is not constant, and so we must have an acceleration associated with the change in velocity, and specifically the change in direction. So let's write the following statement. Despite no change in speed, there is an acceleration. And the reason there is an acceleration, because our definition of the acceleration is the time rate change, basically the derivative of velocity with respect to time. If velocity is a constant, then a is equal to 0. Is velocity a constant in circular motion? No, because the direction is changing. If the direction is changing, the velocity is changing, and so you have an acceleration. That's the justification for it. It sounds a bit strange compared to what we've done so far, but it is consistent. Since the direction is changing, the velocity changes. And since the velocity changes, there must be a corresponding acceleration. All right, so what do we call this acceleration? Well, it's a special kind of acceleration. It's not our usual type of acceleration that we have done up until this point. It gets its own name. It is kind of have two names actually. It is often called the radial acceleration or the centripetal acceleration. And so let's write that down. This acceleration is the centripetal, let's write radial first, radial or centripetal acceleration. And so this acceleration is what we call the radial or centripetal acceleration and is due to the change in direction. All right, but how do we get it? How do we find out the value for this centripetal acceleration? Clearly, we can't just use our standard kinematic equations. Anytime you have no change in velocity in those, you end up with an acceleration of 0. And so how do we quantify the value of the centripetal acceleration? It's actually given by a vector. And the formula is centripetal acceleration equals velocity squared divided by r. That's it. That's it. As simple as that. That centripetal acceleration equals whatever velocity we're going around in a circle with squared divided by the radius of that circle. And that will give us the centripetal acceleration. How do we actually use that centripetal acceleration? Well, it's actually quite easy when it comes to uniform circular motion, which is what we're talking about so far. In uniform circular motion, we have a constant speed. We have no regular acceleration. We have this type of acceleration, a centripetal acceleration. The real question becomes, what happens when we are speeding up going around the circle or slowing down going around the circle? Am I going to have two different types of acceleration? How do I handle those accelerations? Those questions are going to be answered going forward. And so here we're saying that v is our instantaneous velocity, as it's always been. And you know what? I don't really love the instantaneous velocity when it comes to describing the motion of something going around in a circle, because all it basically gives me is a snapshot, as usual, a snapshot of the velocity at some instant in time. But if something's going around in a circle and you look at its velocity at an instant in time, you can't even tell it's going in a circle. Its velocity is tangent to that circle. So even if I'm going like this, at some point it's tangent to that circle, and that is not really descriptive of the circular motion itself. Let's define r as the radius of the path. And I can call it the radius of the circle, but maybe there's not a full circle. Maybe it's just part of one, and so let's call it the radius of the circular path, might be a better one. And so there we go. We got our centripetal acceleration equals v squared over r. Well, if we're talking about an acceleration, we are talking about a vector, and the question is, what is the direction of the vector? Well, it's not the direction of the velocity, interestingly enough. The direction of the centripetal acceleration is always towards the center of the circle. It's kind of descriptive in the name itself, right? Centripetal means center seeking, or radial, right? It gives us the idea of heading towards the center. So let's go ahead and draw some kind of a circular path. That's a pretty good circle, but we'll get rid of that center and make something about here the center. There we go. And this circle has a radius of r, and we're going to make this our path. Our object might be here at one point, it might be here at one point, and it's headed in that direction. So it's going around and around and around and around. And specifically, at any of these locations, the velocity is going to be tangent to our circle. And you know that this is true. One way that you can test that would be if you, again, spin something around in a circle, and then you let it go at some point. It's not a good idea. This is made of wood for me to let this go right now. But you can tell which way it's going to go by Newton's first law as well. It wants to go in a straight line. It wants to go out in a circle. And what that means is if I was to, let's say, cut the string, it's going to end up moving tangent to the circle wherever it is. So for example, if this is spinning around and it gets up here and I let it go, or the string breaks or whatever, it's going to go out in a straight line that way. All right, and that's what that velocity, instantaneous velocity value implies. Another place, or another term we want is our centripetal acceleration. That dot was supposed to kind of be straight up, but it's okay, as long as my centripetal acceleration is always pointing towards the center. And that means that this has to be 90 degrees. That doesn't look quite like 90. Let's see if we can fix that a tiny bit. I'm going to put the circle right here. Then we've got our acceleration, our centripetal acceleration headed towards the center, where that angle there is 90 degrees. And so the acceleration is always center seeking, the velocity is always tangent, the angle between them is 90 degrees. And so now what we want to do is to think about whether this is a good way for us to describe the motion of an object that is going to be accelerating. And the answer is it's not. It's not going to be very productive for us to talk about the motion around a circle using our old-fashioned linear values. V and A, whether it's centripetal or a regular one, these values are really made for describing motion in one dimension or even in two dimensions, but not necessarily in a circle. We're going to find a better way to describe circular motion. But let's make a couple of statements before we do that. We have the velocity is always tangent to the path. And we have that centripetal acceleration is always perpendicular to that velocity and is center seeking. So centripetal acceleration is always perpendicular to velocity Now that doesn't tell us exactly where it's going, because this line could also be perpendicular, and that is not what we're talking about. Not only is centripetal acceleration perpendicular to velocity, it is also center seeking. Like so. All right, so that gives us our description of something going in a circle. But I want to motivate us to realize that this classical construction of using A and V is not that good when we're talking about the motion of something going in a circle. So let's take an example of circular motion. We're going to take my arm, right? So here's my arm. It's going around in a full circle. That's a full circle there. So you get a bit further back. So I'm going off the screen a little bit, but you get the idea. And we can think about the velocity of different parts of my arm as it goes around the circle. Think about the motion of my fist. What is the velocity of my fist compared to the velocity of my elbow? Are they going at the same velocity? Is one bigger than the other? Think about that. Absolutely, they are not going at the same velocity, because the object that is farther away from the rotational center will be going faster. So my fist is going way faster than my elbow. Maybe, for example, let's just say it takes me 1 second to rotate around like this. Maybe the fist could be going around a circumference of 2 meters. And so it would have a velocity of 2 meters per second, for example. But the elbow is not going as much around. It's not going as much around that distance, but it still takes 1 second to go around. And so it must be going slower. And then what about my shoulder? What about my shoulder? What about that center? Is it moving at all? Every point along my arm has a different velocity than every other point, because the radius influences what that velocity is. So what am I getting at is that using our normal linear quantities, v, velocity, a, acceleration, is inefficient when we're talking about circular motion. We need some sort of circular values, some kind of rotational velocity to help us to describe this circular motion. But to do that, we need a completely different coordinate system. We have classically been using the Cartesian coordinate system since we were very, very, very young. And to use a different coordinate system may seem bold, and it is, but it's what's going to be necessary to make our kinematics easier to do. So I gave you this idea of uniform circular motion. I gave you this centripetal acceleration, but what I'm asking you to do now is to actually kind of put it away in the back of your head, because we're going to come back to it, because sometimes you do want to know what the linear velocity, the linear acceleration is, but I'm going to create a whole new kinematic system dependent on a whole new coordinate system to help us to do rotational kinematics far, far easier than A and V will allow. Okay, so now let's introduce rotational kinematics using the polar coordinate system. And so what we're going to do, first of all, is to introduce a new coordinate system which will give us the space we need to create a new kinematical set of equations. And so let's start by trying to describe the polar coordinate system. And so we'll start with our classical coordinate system just as a comparison. And so this is our two-dimensional coordinates in Cartesian coordinate system. It's just y and x. We've been using it forever. And y and x are good at describing the location of point P. This location, point P, can be described typically in the following way. We can say that P is located at some x and some y. And this, again, is from our old-fashioned Cartesian coordinate system. All right, so now what I'm trying to tell you is that I could actually describe where P is located a different way. I can describe P's location with a combination of two other terms. For example, R and theta, where R is going to be this distance here. We're using R here for radius, but for right now, it's just a point, right? It's just the distance between the origin of our coordinate system and the point we're looking for. And theta is the angle between the line that connects the center to P and the positive x coordinate system. So as usual, we'll say that this direction is our positive x coordinate system, and as we go in this direction, we go positive. So let me make sure we've got that. Yeah, okay, so here we go, positive x, and whatever angle we're going is theta. So we're purposely measuring theta from the positive x direction. We've been doing that for angles all year, and this is where it really, really pays off. And so we have R and theta. R and theta are our polar coordinate system. We can describe the location of any point in space with either x and y or with R and theta. Again, R is, let's write this down, the distance from the origin to our point. Distance from origin to point, and our theta is going to be the angle from the positive x-axis. We always start there. And we head in the counterclockwise direction. And where do we end? We end to a line that connects P and the origin. All right, there we go. So we are very, very quickly going to see the power of using this coordinate system. It's going to be able to describe the motion of something a lot simpler. Let me show you that. Let's do the same thing, but this time with 2 points. Let's create our coordinate system once again. And this time we're going to go along a circle. And we'll put 2 points on this circle. Here, we'll call that P1. And here, we're going to call that P2. And so basically, we're going from P1 to P2. We're going around like this, from P1 to P2. And we can describe the motion from P1 to P2 because we know what these two values are. This value can be described as R, theta 1. Let's write that as R1. Let me make that a bit clearer. So we'll call this R1 and we'll call this theta 1 all the way to P2. And P2 also has its own R and its own theta. So let's call that R2 and theta 2. And so we can write our P1 as R1 theta 1 and our P2 as R2 theta 2. And so you look at that and you say, well, what's the advantage? Where does the advantage come from? How is that any better than using x1, y1, x2, y2? The reason it's better is because these r's are the same thing. There is only one r in this problem. If your origin is actually at the center of the circular motion, that's what you do. So if you have some sort of circular motion like this, you will put the origin at the center of the circle, and then if I have any point along the circle, it's going to have a radius of r. That r is constant for the entire circular motion, meaning I have not one thing that changes, not two things that change, x and y, but only one thing that changes, and in this case, it is theta. The theta varies as we go around the circle, but the r doesn't change. The r remains constant. And what we've basically done is we've reduced the number of positional unknowns from 2 to 1. What that means is I'm not going to have a bunch of x equations and a bunch of y equations, and I'm going to do things in each of them and then have to decompose and recompose and all that kind of stuff. I've created a coordinate system where I only have one thing that changes, one position that changes, namely theta. Theta is going to be the key in figuring out what the rotational motion is like, because r is a constant. And so what do we care about? We care about motion as in displacement of the angle delta theta. It's this value here. When you're moving from P1 to P2, you want to know what that angle there is. Let's call that delta theta. Draw it on the other side. This is delta theta. The difference between the two, so you can just say theta 2 minus theta 1. This is, in fact, going to eventually be called angular displacement, but we'll get there in just 1 second. Before we do, perhaps we want to know how far we went. Perhaps you want to know the distance traveled by our point P. Now, if we had an x and y coordinate system and we tried to subtract the two, we would actually end up getting that value there, that red line. Notice that is not the distance traveled. It is the displacement in the xy coordinate system, but it doesn't actually tell you how far around you went. If you want to know how far around you went, well, you have circular motion. You're talking about this quantity here. This is known as delta S, and it is called arc length. So when going around a circle, it's typically, if you want to know how far you went around that circle, we talk about arc length. And we can calculate arc length pretty easily. This is just a geometrical formula about circles, no physics here yet at all. But delta S is just equal to R times delta theta. And to be honest, people usually don't even write the deltas in these sorts of problems. You'll often see this written as S equals R theta. And that gives us our value for how far around the circle we went with basically just one changing value. You know the radius of a circle, and so what's left is theta. How far around in angle displacement did we go? Multiply that by the radius, we get the actual arc length or distance traveled. Now, before we go any further, the obvious question is, how do you multiply a radius by an angle? Radius has the units of meters. Theta typically has the units of degrees. Meters and degrees don't really go together. What this coordinates system is going to need is radians. This is all in radians, not in degrees. And so we're going to measure this change in angle in radians, and then multiplying radians by meters actually gives us meters. Radians are a unitless quantity. And so we have the basis now. Our polar coordinate system is the basis for us to develop a rotational kinematic system around. And so let's do it. And this is going to seem very, very familiar to us because we've already developed a kinematic system. We did one in one dimension at the very, very start of first year physics. And now what we're doing is doing it again. And so instead of calculating the displacement, x, I think originally, or y, or s, or r, we are doing angular displacement. And angular displacement is theta. We've already created it. It's really delta theta, but for us, we're just going to call it theta, because theta is going to be, just as we have defined in our polar coordinate system, it is the change in angular position in the polar coordinate system accounting for multiple rotations. What does that mean? I'll show you in a second. All right, so what do we mean by multiple rotations? Well, this is actually different than our regular displacement. Recall when we did our regular displacement, we didn't care about the distance traveled. We just wanted to know where we started and where we ended up, and who cares what happened in between. The difference gave us our displacement, and we were good with that. Here, you actually do want to know how many times around you go. So for example, if I had my object starting here and it went around one time, two times, like that, I actually care about that. The angular displacement here was 2 rotations, or what we would call 2 revolutions, or in terms of radians, well, let's see, there's 2 pi radians in each revolution. So 2 pi radians go into one circle, just like 360 degrees go into one circle. If I go around 2 times, that's 4 pi. 4 pi radians. 2 pi, 4 pi. The displacement typically you would think is 0 because you start and end at the same place, but that's not how circular motion works. You have to account for how many times around you go. So let's try it again. Actually, let's do it in the proper direction from the positive direction. Okay, here we go. So we're starting on our positive x-axis and we're moving in this way up to here. Now, what kind of displacement is that? Well, that was a 90-degree change. What is that in radians? Well, we know that to convert it into radians, that would be 1/4 of a circle, or pi over 2. We know pi over 2 is 90 degrees. And so here we go. That's pi. one more time, let's say we end up going around once, twice, and stopping about there. And so we went around 2.5 times, which would be 2 pi, 4 pi, 5 pi. So 5 pi, and that's literally 5 times 3.141, etc., is the amount of radians that we have traveled. And we'll get a lot more experience with that as well. But for now, we also want to know, or at least write down, our units here, which is radians. We write it as rads, and that refers to radians. Okay, great. And so the next thing we want to do is to expand our displacement definition to start thinking about speed and acceleration. So the next thing is obviously angular velocity. If you've created an angular displacement, you want to know how fast that displacement is changing. And angular velocity is given not by v, but by a new term, fancy letter W, also known as omega. Some people say omega, some people say omega, and that term is going to define how fast we're going in a circle. And so again, displacement just tells us how far we went. Went from here to here. That's 90 degrees or pi over 2. I have a theta of pi over 2. But I want to know how fast I went. How long did it take me to go from here to here? Well, if it took you 1 second, let's pretend for a second. So I have pi over 2 displacement in 1 second. And so that's pi over 2 radians per second. Let's try something a bit more complicated. Let's say it takes me 5 seconds to go around 10 times. All right, here we go. I'm going to get going, and I'll tell you when I start. And go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I did 10 revolutions. And a displacement of 10 revolutions, 10 times 2 pi is 20 pi. And let's pretend that it took 5 seconds. So 20 divided by 5 is 4, right? And so my speed would be 4 pi radians per second. That's an average speed, as we will see. And so we're going to define angular velocity in its more technical form, omega, as the time rate change of angular displacement. Just as v was the time rate change of regular displacement, our angular velocity is the time rate change of angular displacement. Is that a formula that we will really use? Not so much. We will actually derive formulas that give us a better relationship. But the SI units for angular velocity, well, clearly we have a change in displacement divided by a change in time, or radians per second. And it's usually written like that. Sometimes people will write it without the radians, because radians really is not technically a unit. It's not like meters. Radians is a description of how much of a circle you have. What fraction of a circle do you actually have? And so sometimes they'll leave off the radians, and it'll often be written as 1 over s, or s to the negative 1. It's unlikely you'll see that in first year, but you may in upper years. And so let's think about this value, this radians per second. So now I'm describing radians per second, how fast something's moving around. Have you ever heard those units before? Is it the kind of description that we use in our everyday lives, or even in engineering or science, etc.? Not so much. But there is a unit that is commonly used to describe the angular velocity of something. And I'm sure you've all heard about RPM, or revolutions per minute. Revolutions per minute is just a more commonly everyday used unit of measure, but it's not the SI unit of measure. But we should learn it because it is commonly used, whether you're talking about a disk drive in a computer, some kind of medium like a record or a CD or something like that. Revolutions per minute is commonly used, a ride at an amusement park, etc. So let's make a note here. And it's almost like the difference between meters per second and kilometers an hour, right? We use kilometers an hour in our everyday lives, but clearly meters per second is the SI unit that we care about. So let's say that RPM, which is just revolutions per minute, is commonly used. And so what we need to be able to do is to go between the two of them. Sometimes we're going to give values in RPM, sometimes in radians per second. If it is given in revolutions per minute, it's almost certain you need to convert it into radians per second to do your mathematics. So how does one do that? How does one go from, let's say, 1 revolution per minute? Let me make that a bit neater. 1 revolution per minute to radians per second. Well, what you basically do is you multiply by 1/60, and that is because 1 minute equals 60 seconds, and so that minute will cancel that minute, leaving us seconds. That's good, but you must also multiply by how we convert from revolutions into radians. And so this is super, super important for you to have at the tips of your fingers. Not only is a full circle equal to 2 pi radians, it's equal to 360 degrees, and it's equal to 1 revolution. 1 revolution means that we are making 1 full circle around. And so our unit is going to be 2 pi radians is equal to 1 revolution. And so here, and we're finally left with pi over 30 radians per second. Now, I've been giving a lot of things in terms of pi, mostly because I can't multiply by pi in my head, right? That's very hard to do. But when you're giving values in rotational kinematics, you should not be leaving your final answers in terms of pi or in terms of fractions. You should be using decimals. And so let's throw that into our calculators and make sure we understand how one uses pi. Pi is literally on your calculator. It's that button that will give you 3.141 something. So I don't know too many digits. Throw that in there and then give your final answer with the right number of significant figures. This is given with 3 significant figures, and so your real value here should be 0.105 radians per second. So 1 RPM equals 0.105 radians per second. So, and there's more digits than that. It's not like a perfect conversion, but it's good enough for 3 significant figures. And so that's pretty easy for us, I think, to understand how the angular displacement is just our motion around the circle. That angular velocity is how fast we're going around the circle. The thing that is the hardest, I think, to really appreciate is our next term, which is, of course, angular acceleration. Angular acceleration also is not given by its traditional letter of A. When we're talking about angular acceleration, we're going to use the new term alpha. And alpha is going to describe basically the rate at which we're speeding up or slowing down. And so even when we have a nice, easy problem, like let's say a car is at a red light and picks up speed, gaining up to 60 kilometers an hour or something like that, you can calculate the acceleration pretty easily. But you will eventually be able to do the same thing for circular motion. So for example, this object right now is not moving at all. It is at rest. Eventually, it will turn on and it'll start going faster and faster and faster and faster and faster and faster, and soon it has reached its top speed. And so we can quantify the increase in speed, the time rate change of angular velocity, using this term alpha, angular acceleration. Let's do that. So angular acceleration is given by alpha. Alpha is equal to the time rate change of angular velocity with respect to time, which, for those that are paying attention, is the derivative of a derivative of angular displacement, or the second derivative of angular displacement with respect to time. So let's call this the time rate change of angular velocity. All right. And so the best way for us to really appreciate angular acceleration, whether it's something that is going fast around a circle and slowing down, or the opposite, is to use it in practice. And so our angular acceleration is given through our SI unit clearly of, well, we've got one more divided by time, giving us radians per second squared. And again, in rare circumstances or in later years, you may see it written like that because, again, the radians is basically unitless. And that's going to be important, you'll see, when we do some of the math that we end up doing. All right, so what do we have? We have new kinematic terms. For the first time since the beginning of first year physics, we are now introducing new kinematic terms. We want to be able to describe fully the motion of an object going around a circle, whether it's traveling at constant speed, picking up speed, slowing down, etc., with the terms theta, omega, and alpha. Learn those words. We're going to use them quite a lot. I won't be talking about fancy letter W. I will be saying the words omega. You should know which one I'm talking about, not just by being able to see it on sight, but to understand that that's angular velocity. Theta is angular displacement. Alpha is angular acceleration. And so the question is, what do I do with these terms? What do I do with problems where I have some of these values and I want to find other values like that? How hard is it to do those problems? Well, I'm telling you right now that doing rotational kinematics is as easy as doing one-dimensional kinematics. It's far, far easier than doing projectile motion, because here's the question for you. Is theta a vector? Is omega a vector? Is alpha a vector? Do they have components? Do I need to decompose them and recompose them as I did with my vectors for projectile motion? The answer is no, I don't need to do that. And as for whether they're vectors or not, the answer is kind of. They're kind of vectors. They're a kind of vectors called pseudovectors. And pseudovectors are super easy because pseudovectors can only go in one direction or the other. Think about this. What is the direction of angular displacement right now? Well, you're thinking to yourself, it's around a circle, right? But which direction around that circle? And what other directions can theta go? Well, it turns out theta can only go in two directions. It can go this way, or it can go this way. And if you define one of those directions as positive, well, then the other direction is negative, and that's it. So theta doesn't really have a direction in the traditional sense. It's kind of like doing one-dimensional kinematics. If you recall, with one-dimensional kinematics, in the x direction, we're either going in the positive x direction or the negative x direction, and that's it. We don't have to take into account any components or anything like that. We're not talking about vectors that are going in some odd direction. Our rotation's either rotating this way or it's rotating that way. And that's it. And so it is not a vector. These are all pseudo-vectors. And we're going to describe them as not really vectors. Since you can only go one of two directions. You can only go clockwise or counterclockwise. If we define one of those directions as positive, then the other one is negative. And so we will define those as positive and negative. All right, so we've got ourselves the beginnings of some very, very interestingly new, yet not that challenging rotational kinematic problems. I want to look at now omega for my arm. So we talked about the velocity of my arm as it goes around the circle and the fact that my fist is going faster than my elbow, going faster than my shoulder. But what if I describe my motion not with v, the linear velocity? What if I described it now with omega, our new angular velocity? Do I have different angular velocities for my fist compared to my elbow? No, it's exactly the same. It's exactly the same because now we're defining the displacement not as how far we went in meters, but how far we went in degrees. And my elbow and my fist, every part of my arm is moving around this circle with the exact same displacement. So every part from here to here went around 90 degrees. 90 degrees from here to here. That's 90 degrees or pi over 2. Doesn't matter if you're my fist or my elbow. It's going to be the same. Therefore, the angular velocity of those is going to be the same. Therefore, the angular acceleration of those is going to be the same. And as far as the direction goes, it's either this way or it's this way. It's either positive or it's negative, which means we don't really have to do any vector work for these types of problems, which is going to make them fairly straightforward. When you get used to rotational kinematic equations, it should be no harder than doing free fall, for example. And so let's introduce the actual equations themselves. I've been hyping them. Let's see what the rotational kinematic equations actually are. And we're going to not derive the rotational kinematic equations because the method of derivation is exactly the same as what it was for the linear kinematic equations. And so what we can do instead is just to introduce them. And so the rotational kinematic equations are going to be the following, but we're going to not use x initial and x final like we used to, we're going to set our initial position to 0. So when we did our kinematic equations, we always had x initial in there, and 95% of the time x initial was equal to 0. But this time I'm actually forcing it to be equal to 0. Wherever we start our problem, that's our 0 point, meaning that our final position is going to just be called theta. And so these equations are going to be identical to our one-dimensional kinematic equations, as we'll very, very quickly see, with omega final equals omega initial plus alpha t, which is exactly the same, if you recall, as v final equals v initial plus at. And our second equation, I remember was that one, x final equals x initial, etc. But if x initial is equal to 0, then we just have theta equals omega initial times t plus 1/2 alpha t squared. And this is exactly the same as x final equals x initial plus v initial t plus 1/2 at squared, or you could just write it like this. Delta x equals v initial. I'm just writing this small because I'm not reintroducing these equations. I'm just reminding you, you've done this already. We've derived this. We've done these numerous times. These linear equations, you know them well. You're good at them. And now we're just seeing them again in a slightly different form. Our final angular velocity is equal to our, you know this, initial angular velocity plus 2 times acceleration times the change in displacement. And you commonly know this as Vf squared equals V initial squared plus 2 times A times a change in x. There we go. And so we have 3 equations once again. The relationship between the different terms is exactly the same as it used to be. Exactly the same. It's just understanding the new terms, understanding what theta is, what omega is, what alpha is. That's the new thing here. But the skill set that you've already developed is going to translate directly into doing these problems. You will only need these 3 kinematic, rotational kinematic equations to solve any problem. And so why don't we do an example of a problem just to get our feet wet now with using these rotational kinematic values. Again, they're analogous to our velocity equations here. And so I want us to try the following as our first rotational kinematic problem. We've got ourselves a dentist's drill. And the dentist's drill is rotating at 5,500 RPM. So we're giving our units in revolutions per minute. Let's say the dentist is done drilling and turns off the drill. The dentist turns off the drill. Now, it doesn't instantly come to a stop. It takes some time. Let's say the angular deacceleration of the drill is, let's use 220 radians per second squared. Much harder to make these problems and much harder to assess if your answer makes sense because we are far, far less familiar with these sorts of terms. But your question is, how long does it take to come to a stop? All right, so a dentist drill is rotating at 5,500 RPM. The dentist turns off the drill. If the angular deacceleration is 220 rads per second squared, how long does it take to come to a stop? And we're not really familiar with this sort of language, and so this question can seem perhaps a little bit intimidating. But if I was to reword this in a more familiar one-dimensional way, let's say in the x direction, it would be something like this. A car is driving at 120 kilometers an hour. The driver hits the brakes. If the deacceleration is 7.5 meters per second squared, how long does it take for the car to come to a stop? That will be super easy. That will be a super easy one-dimensional kinematic problem, and I'm arguing that this problem is also a super easy one-dimensional pseudo-vector easy problem. We're doing a two-dimensional problem, but by having our coordinate system the way it is, we can answer this question without too much trouble. In fact, some of the most challenging parts of these types of questions that students first find is identifying what you actually have, identifying the terms you're given until you become familiar with the vernacular and the implied values. It can be a little bit challenging, but that can be quickly overcome with practice. Practice, 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 practice. Try as many rotational kinematic problems as possible. Okay, let's actually get into this value or this question by writing down some known values. What do we actually have in this problem? Okay, the first thing I have is it's rotating at 5,500 RPM. What is that? What value are we actually given here? RPM, let me think. Revolutions per minute. That is a angular velocity. I know how fast the drill is going initially. And so let me write that down. We are given, by the way, I'm not going to draw a picture for this. This is one place where diagrams are not that helpful. What am I going to draw? A circle and then another circle? I'm not sure exactly. And so I'll skip that part. I'm going right to my identification of the values that I'm given. I'm starting with 5,500 RPM. Do yourself a favor, pause this video and calculate that in radians per second. This is a problem typically done in SI units. I am not going to do any math with RPM, just as I wouldn't if it was kilometers an hour. And so convert it to radians per second using the method that was shown earlier. Do that now. Okay, let's check our work. Keeping a couple of extra digits around just for safety. I get 576, but I'll write it as 575.96 radians per second. Far more accuracy than I need. I probably should have rounded before, but it's okay. What else do I have? Well, the dentist turns off the drill and it says directly the angular deacceleration. The angular deacceleration. What term is that? Well, deacceleration is a form of acceleration which is part of alpha, or angular acceleration. The units are given in rads per second squared. If I look up at my work for the angular acceleration, I know in SI units it is rads per second squared. So even if I didn't recognize the words, I certainly recognize the units. I know that it is in radians per second squared, and so this is an alpha, that's for sure. Equals 220 radians per second squared. Okay, do I know anything else? What's that? You notice the problem? You notice the problem? Yes, I purposely made a little error, which I was hoping you'd pick up on. If you haven't yet, look carefully, and we'll take it up when we finish our list. Think of a completely different value that we have. I don't have any other numbers here, but it does say how long does it take to come to a stop? How long does it take for my angular velocity to become 0. That is the speed of something that has come to a stop, whether you're in linear or in angular, and that means that omega final must be equal to 0. Our final speed or our final angular velocity is 0 here. And then finally, what are we actually looking for? What does the question want? How long? How long does it take to come to a stop? It wants to know the time. It wants to know what the time is. I assume it's going to be very small, but it'll take, we'll see what that value is soon enough. All right, so as I said, I made a little error. Were you able to find it? Well, it turns out that one of our values needs to be negative, and it is most logical for it to be the acceleration. The acceleration is slowing our object down. It's coming to a rest. If we assume the direction that it's spinning in is the positive direction, and it comes to a halt, then the acceleration has to be in the opposite direction. Let me demonstrate one more time. If I have an object spinning around at a high speed and it eventually slows down and stops, the velocity is the way that you're seeing the object. The displacement is in the same direction that you're seeing the object go. But if it's slowing down, then the acceleration is in the opposite direction to the velocity, opposite direction to the displacement. If the object is speeding up, then it's in the same direction of the velocity, the same direction as the, not necessarily the displacement. And we'll see examples where that's not the case, but certainly with the velocity. So what I'm trying to point at is if my velocity is positive, which I think is what you should set it at, then your angular acceleration is negative. And so if you didn't see that, if you didn't get that, you would get a far, far different value. In fact, you'd end up getting a negative time. So let's see what we do get. Which equation should we use? First of all, go ahead and have a look. Notice I don't have theta. I'm not asked for theta. We stay away from any equation that has theta, and so I clearly go with equation number 1. And equation number 1 is that omega final equals omega initial plus alpha t. This value is 0. We rearrange our equation by moving omega initial to the other side. I've got alpha t like this. Divide both sides by alpha, giving us t equals negative omega initial divided by alpha. Let's throw that into our equations. And so we have minus, let's see, 575.96, all divided by alpha of negative 220 radians per second squared. Clearly, if I did not have alpha as a negative, I would have got a negative time. That would have clued me in that something is wrong. I would have gone back and looked at it and figured out that we had the wrong sign on our acceleration. So everything is looking good. I want to kind of make sure that I end up with seconds. This is the first time I'm doing a problem with rotational kinematics. Let's make sure. So this is radians per second divided by radians per second squared. And so that cancels that, cancels that, cancels that. And I'm left with 1 over seconds, which is seconds. All right, good. Get rid of all of that. Just checking to make sure units make sense. They do. And throwing your values into your calculator will give you something like 2.618. But let's round that to 2 sig figs of 2.6 seconds. And that's it. It takes 2.6 seconds for the drill to come to a stop. And that seems about right. It's certainly when the dentist first turns on the drill, you kind of freak out a little bit, right? It's just me. Maybe it's just me. But it's just like that. Oh my gosh. And so when they turn it off, same sort of thing. it feels like it takes a little bit of time. All right, so let's try a part B for this problem. We didn't give it yet, but the only thing left to find, there's only one thing left to find. So I ask you this question. For the same problem, how many revolutions did the drill make as it came to a stop? So how many revolutions did the drill make as it came to a stop? So basically, I want to know, as that drill was going around and it got turned off, it's still going to go around more and more and more as it slows down, comes to a stop. So if this was our one-dimensional analogy, the question is just saying, hey, remember the car example I gave you? It's just saying, well, how far did the car travel as it came to a stop? That's the exact same problem. What are we looking for in this problem? Even though it doesn't ask for angular displacement, it wants to know how many revolutions. That is a distance. That is an angular distance or an angular displacement. And so you're looking for theta. You want to know what theta is. And we'll eventually have to put it into the units of revolutions. But for now, let's find theta. And so what equation should we use for theta this time? Not equation 1. So equation 2 looks good. Equation 3 also looks good. I'm okay with either of them. I'm going to go with equation 3 as I always do in these sorts of circumstances. Just in case I made a mistake in part A with my time, I can go straight to equation 3 and not worry about if there was a mistake made. But equation 2 looks just as good, if not easier. And so here I go. How many revolutions did the drill make as it came to a stop? Equation 3 is written as omega final squared is equal to omega initial squared plus 2 times alpha times theta. My omega final is 0 as it was before. This time I'll move my negative or my omega initial squared to the left-hand side, making it negative, and that's equal to 2 times alpha times theta. And so I just have to divide through by theta. Super easy. The mathematics, the algebra, all this kind of stuff is like an easy one-dimensional problem. And so we just have negative omega initial squared, all divided by 2 times alpha. That's it. Throw those values in, see what you get. Pause the video here and see if you can find out theta, not just in radians. That's what this is going to give you in radians, but eventually in revolutions. Let's see how you do. All right, this is how I'll finish the problem off. I'll take my initial velocity in radians per second, square it. The negative stays outside. That's key for these sorts of problems. The negative was already here. It stays outside. Omega initial was a positive value. Times 2 times my negative 220. Throwing that into my calculator to see what I get, I'll end up with a theta of 753.9 radians. That's a pretty big number. And I'm certain it is radians, but I can do a quick check just because I'm new to this sort of thing. So I had a rads per second squared, and I divided it by a radians per second squared. Yeah, so the seconds will cancel out. One of these rads will cancel that, and we're left with just radians. Excellent. All right, so now I've got my theta in terms of radians, but recall the question asked for how many revolutions. So that told us what the units it wants is. It's almost like if the car said, in how many kilometers did the car come to a stop, right? It's telling us, okay, it wants to know the distance, but it wants it in kilometers. Well, that's the angular displacement in radians. And so how do we go from radians to revolutions? We do the opposite of what we did for RPMs, but We don't have anything to do with time. It's simply the ratio that 1 revolution equals 2 pi radians. Make sure you have the right thing on.
Hey, oh, where's my body gone? Okay, no one panic. We can still finish this problem off. Let's see. So our rads here are going to cancel out, leaving us with 753.9 divided by 2 pi, which is 120 revolutions with 2 sig figs. And that is our final answer for angular displacement.